And in last lecture, we considered homogeneous linear second-order ODE with constant coefficients. And Euler-Cauchy equations is another type of homogeneous second-order linear ODE, which is simple, so that we are able to solve this ODE. Okay, so by observations, you can see that this ODE is not in the standard form because the coefficient of y sub prime is not equal to 1, so it's not in the standard form. But from this ODE, it is suggested that the solution might be a polynomial, okay, of x. So, so we substitute the nth power of x as possible solutions. So y prime of x is equal to n, xn minus 1, and y of x is equal to n minus 1, xn minus 2. Okay? So we plug this formula into the ODE. We find x squared n minus 1, x n minus 2 plus ax n x n minus 1 plus b xn equal to 2. Okay, now you can see all three terms has a factor which is equal to x to the nth power. Okay, so we have less than n minus 1 plus an plus b equal to 0, or we can combine linear terms. So we have n minus 1n times b. Okay, so we conclude just like in the case of having constant coefficients. Ys is a solution of this the Euler-Cauchy equation, right? You can only and satisfy the quadratic equation. N squared plus n minus 1n plus b. Okay, so this is given only condition. Any questions? Okay, now, so we solve n1 into equal to 1 half of 1 minus a plus square root of 1 minus a square minus b. Okay. And the m2 is 1 half of 1 minus a minus square root of 1/4 1 minus a square minus b. Okay. Alright, so now we have 3 cases to consider. Case 1, m1 and m2 are distinct real. When they are distinct and real, then y1x, which is equal to x to the n minus power, and y2x, which is equal to x to the m2 power, linearly independent solutions of the Euler-Cauchy equation. Right? So if m1, m2 are distinct or real, then these 2 functions are linearly independent solutions. Okay. And a general solution is C1 x to the n1 power plus C to x to the n power. So we get so we solve the Euler-Cauchy equation. Okay. So case number 1 is quite easy. Case number 2, m1 is equal to m2 is equal to 1 half of m minus a. Maybe we have b equal to 1/4 of m minus a squared. Okay. Now in this case, all right. In this case, we okay. So first of all, we write the Euler-Cauchy equation in standard form. Alright? So we write the Euler-Cauchy equation in standard form, so we have to divide the equation by x squared. So we have y to the front plus a divided by x y front plus b, but b is equal to but t is equal to 1/4 of 1 minus s squared. Yeah, remember b here. And so in this case, we have this equation. So our Euler-Cauchy equation in standard form, then we can like this. Any questions? All right. And with y1x which is equal to x to the, correct? X to the half of 1 minus x power, the solution. Okay, so now we have a solution. So we can apply the method of reduction of order here again. Right? So by the method of reduction of order, okay, relate y2 equal to u of y1. Okay. Now here, this is equal to e of x. Right? So so we know then u is equal to, remember that, with equal to square okay. So this u takes the integral of the capital U, and the capital U is equal to 1 over y1 squared times the exponential function of minus the integral of g of x. Okay. Right. This is from our derivation in the method of reduction of order. Okay, so p of x, now p of x is equal to a divided by x, implies that minus p of x dx, which is equal to minus a, okay, and the logarithm of x here. So okay, so this implies that okay, is equal to 1 over x power. And then u is equal to square. Okay. And this is equal to 1 over 1 minus 8. So this is equal to 1 over x. Okay. So capital U is equal to 1 over x. Alright, so finally u is, this is equal to the natural logarithm of the x value of x. So implies that y2 of x is equal to u of x, y1 of x. So it's equal to x to the 1 minus 8 power. Okay, and no reason. Okay, which is linearly independent. Y1. Right. general solution of the Euler-Cauchy equation is equal to C1 plus C2. Let's do out. So this is the general solution. Any questions? Okay. Now, the final case. N1 and N2 are complex quantities. It's better to take an example. Okay, so it's better to take an example. Okay, so we consider 0.6x micron, 16.04 y over 0. Okay. Yeah. So we have to solve the following equation. Okay, so we have to solve such a equation, and we find M1, which is equal to 0.2 plus 4i, and M2 is equal to 0.2 minus 4i. Okay, so we have two complex conjugate roots in solving this quadratic equation. Okay, now the two nominal solutions. Okay, the two nominal solutions. Last night I mentioned nominal solutions, right? So the two nominal solutions are this or DE or okay x2, so y1 delta is equal to x in 1, and which is equal to x 0.2 plus 4i, okay, and this is equal to x 0.2 times x 4i. Now, okay, 4i here. So now we can use the exponential functions. So this is 4i times the logarithm of x. Okay. You can see x actually is equal to, okay, right? X actually is exponential of the logarithm of x. Right? Okay, so you have 0.2, so we have I equal x here. The intention is I want to use the Euler formula again. I mentioned last time, right? So this is equal to x 0.2, Then we have cosine 4. Okay. That's I, sine 4. Okay. So now, so we have the real part and the imaginary part. Similarly, another nominal solution is x and 2. And so x equals 2 minus 4i. Okay. And by the similar argument, you can see that this is equal to x equals 2 and cosine 4 times natural logarithm of x minus I sine 4. Yeah. Okay? Now, from these two nominal solutions, so it suggests that y1 x, which is equal to x 0.2 cosine 4 x 0.2 sine. Okay. Are solutions of the Euler-Cauchy equation, which are linearly independent, of course. Okay, so it suggests, and we have to check. In this case, it just suggests. So we check that, and okay, so checking for okay for y1 x okay. Alright, I think the checking is usually the derivative. First of all, this is 0.2 x minus 0.8. Okay. Cosine 4 okay, plus 2 sine minus okay. And y comes to front, and you can see that this is minus 1. So what you have is that okay, and then you take it down. This is x minus 0.8, 0.2 sine 4 minus 4 sine. So these two terms has a common factor, x to the minus 0.8. now for the prime, for the double prime we have 1.8. Okay, and here some plus 8, and here for this one we have minus 0.2 sum 4 something, and the derivative is 4, and multiply with 4, so this is 0.8. Okay. And here it's sine cosine, so this is 16 cosine 4. Okay, and because this is the 1 over x, so you can see that you can put here in the limit. Is that okay? Too fast. Initially we have here, because of the derivative of the natural logarithm. Okay. And we can absorb this factor into here. So I just limit of it into here. So is that okay for you? Okay now? All right, and so we can do some combination. For first of all, we have x minus 1.8 here. Okay, and for cosine, we have two cosine for logarithm of x here. And so we have minus. So we have minus 16.16 cosine. Okay. If I have any calculation error, please let me know. And for sine, we have these two terms. So we have 5, 4. So this is the 3.2. And minus. Okay, so we have 2.4. Okay. Now, so now x squared one. Okay, so you multiply with x squared. So an x squared we have 0.2. Okay, 0.2 here, and and x, and the a is 0.6, so x 0.6 and y prime. Okay. Now, so y prime here, so we have x 0.2, okay, 0.2 here, and so this is 0.12 sine 4. Right. And here we have sine 4. Okay. And this one. And the final term. This is speed, right? So 16.04 times 1. Okay. And the y1 is equal to this one. So we have x 0.2 and 4 and cosine 4. Okay, so now you can see when we add them together, we find that they cancel, right? These two terms cancel. Because they have x to the 0.2 power, they have a common factor right here. And for here, this is 0.12 plus 0.04, so we can cancel them. So conclude that x squared plus x 2.6 plus 16 or 4. Okay. So we have done. Because this is correct, right? After some basic calculations. Okay, so we check that that y1x okay. Now first check y2x. Okay, so that. Okay, so basically we solve the Euler-Cauchy equation. Any questions? No questions. All right. So let's move on. Okay, in this section, we will settle the existence and uniqueness of solution of second order linear. Okay. Right, so we'll settle the question. All right, and well, first we will state the theorem. So sometimes people say this is the resistance and uniqueness theorem for second order linear ODE with initial conditions. Okay, so the statement. The reason why we have to state such existence and uniqueness theorem is that even though we have applied technique to solve several classes of homogeneous linear second order ODEs, we still don't know can we solve any arbitrary second order linear ODE. Right. So the question is there, does there exist any solution? This is the first question. If it does, then we will ask, is the solution unique? Can we find other solution to satisfy the ODE? So now the theorem settles these questions. So consider linear ODE of second order. Okay. Y from plus P of x, y from plus Q of x, y equal to Rx. And this is 2.6.1. The equation 2.6.1 is the linear ODE of second order in standard form. Right? With initial condition. Right? Y x is 0 equal to x 0, and y from x is 0 equal to 1. Okay? And we call the formula 2.6.2. Okay? So we consider such an initial value problem. Okay? So an initial value problem consists of an ODE and two initial conditions. Now, if P of x, Q of x, and R of x, okay, so if P of x, Q of x, and R of x are continuous functions, okay, on an open interval, say I0, and x0 is in this interval. Okay, then the initial value problem is consisting of one 2.612 as a unique solution. Y of x on the interval. Okay, so this is the statement. Okay, so we are talking about initial value problem. Okay, given a linear second order ODE and the two initial conditions. If the two coefficients, Px, Qx, and Rx are continuous functions on an open interval, and x0, which is used to specify the initial conditions, is in the open interval. Then the initial value problem has a unique solution. The interval IC. We will not give a proof here, but a proof will be given in chapter 4. Okay, so we'll give a proof in chapter 4. When we consider, yes, it's. Oh, okay, I already erased here. This is 2.6.1, and this one is sorry, I'm sorry. This equation is 2.6.1. So in chapter 4, we were given the existence and uniqueness theorem for general ODE. Right? Not only for second order, any order. Okay, and maybe non-linear. Okay, so we will give a very general result in chapter 4. Okay, but currently, I will state the theorem specifically for linear ODE of second order with two initial conditions. Okay, so now relate right. So suppose we are facing with a homogeneous linear ODE. And we recall that a general solution of the homogeneous linear ODE of second order y from plus q of x, y from plus q of x, y equals 0. So we name it to be equation 2.6.3. Okay. Alright, so a general solution of the homogeneous linear ODE of second order is made up from two linearly independent of 2.6.3. Okay. So from two linear independent solutions. And give a remark, right? We say that two linearly independent solutions, y1 and the y2 and equal. It said to form a basis our fundamental system. Of solutions of two-point system. So usually, when we refer to linearly independent solutions of this homogeneous linear ODE of second order, we are talking about, say that these two solutions form a basis, right, of solutions of this order. Sometimes people use fundamental system. Well, but you can exchange the word. Sometimes you say basis, sometimes you say fundamental system. Now, in previous section, we give a definition, right? What the definition is that two solutions are linearly independent. But it's very important, how do we know? Can we develop a technique? Two solutions how do we know linearly independent? Zero. So that y1 and y2 form a basis of all solutions of the homogeneous linear ODE of second order in 2.6.3. So this is we always face with such a question. Okay. All right, and I talked about some points to verify whether two solutions are linearly independent. In the following, we will develop an efficient technique to justify two solutions to be linearly independent. Okay? First of all, we will see a necessary condition. we first, right, examine a necessary condition. Alright, so suppose that y1 and y2 are linearly independent. Right? i.e., by definition, there exists K1 and the K2 not both 0, okay, such that K1 y1x plus K2 y2x equal to 0 on I0. Okay, so this is the definition. Okay, we can find two constants not both 0 such that this linear combination is equal to 0 function on the whole interval. Okay? So now, we have either, you can see that y1x is equal to K y2x and I0, or y2x is equal to L y1x and I0. Okay. Yes? Yes. Oh! Okay, so thank you to remind me. So we have 5 minutes break.